So let's see how this looks then in this further experiment. So what we see here is the W. Here are the different actions from go left to go right. And on this side, we have the different colors that I've showed before. And this is just an animation of how the weights stabilize and learn and converge to this situation. What we see is that for these 3 patches here, these are the patches above and close to the light. Here we see that how the associations are learned. We also see that then in this region here, we still learn about the patches. So if we look at how the activation looks now, what we first can look at is the prediction of the behavior. So we have here the unconditioned response that then is followed by the conditioned response. So no, the reverse, the conditioned response precedes the unconditioned response, like we have seen in the rabbit experiment, the air puff conditioning. If we look at the prototype, we also see how now the prototype corresponds to what I see. And there are 2 things here. On the one side, we can see that the pattern is completed. So even if I have here only half of the image, I have here the complete image. And the other thing we can notice is that the response to the patches that are relevant for the task is higher than the response for the patches that are not relevant for the task. So that is just not the perception that plays a role, but that's what the behavioral influence on the perception is. I learn about stuff that's important for me. So there is a balance of this percept. What's it up, Anna?
2 minutes. I don't want to interrupt you, but I'm also doing this with Paul. 3 minutes.
Yeah, but
You know it didn't. Sorry.
I need more than 2 minutes. I'm sorry.
Yeah?
Yeah.
Let him go, let him go.
We run the experiment over different parameters, different trials, and to analyze the results, we have defined 2 measures. One is the behavioral performance, so how well do I actually learn the behavior to go towards the light. This is just like the percentage of trials that end in this area around the light. Then we also have perceptual performance. So in this case, the behavioral performance is 97%. Then we have also the perceptual performance, that we take the prototypes we have learned and we test how well we can classify what is actually was the percept corresponding to this prototype. And in this case, I'm showing here, whenever I can classify it, I have a green circle. When I cannot classify it, it's a red circle. And in this case, the performance is 79%. If I do this for the different parameters and then just plot the performance I get in this matrix, so here I have zeta going from 0.7 to 1, and you have a rho going from 0 to 4. So this means the higher rho, the higher the impact on the behavioral prediction. I see that I have in this region a high performance in the behavioral measure. But then if I do the same for the perceptual performance, I see that exactly in this region where I have a high performance for the behavioral part, I have a low performance for the perceptual measure. But still then the other part is very high for all the parameters, so it's not very sensitive to these parameters. If I just multiply behavioral and perceptual learning, so this is just a multiplication of this value going from 0 to 1 and this value going from 0 to 1, I get the region where both behavioral and perceptual learning perform well. And we see that there's a quite broad region around here where we can have both perceptual and behavioral learning in the same moment. What's now the next question is, how does the system deal with changes? We have looked at 3 different changes. In the same experiment, in this case just with two different start positions, we can exchange the cues, or we can exchange the destructors that are the patches that are not relevant. So I exchange the cue with a distractor, or I can turn the light on and off. And I can then look again in the first trial. I do 200 trials of learning, so I learn the task first. Then I perform the switch. Then I learn the correct behavior for the switching. And then I again turn it back to the original position of the patches and the light. And I have the relearning. To normalize the weights, I have 200 pre-trials. At this point in time, I just scramble all the weights. So what I can assure like this is that the weights here has the same statistics as here and as here. If then look at the behavioral and perceptual performance just in this part, what we see is this. So we have here for different conditions, I plot the behavioral performance for different values of rho. These are the trials. What we see is actually that for a value of rho above 0.1, I recuperate from the switches very fast. And the faster I recuperate, the faster, the higher the rho is. If we then look at perceptual performance, I see that actually perceptual performance even only degrades a little bit within the shifts in the moment I shift, but then recuperates very fast and is stable for the whole rest of the trial. So what's interesting here, what we have to appreciate this result is that the W changes completely. So to associate the different percepts with the action, this W has to change, has to remap. But still, if we then look at the prototype, because it is a projection, the prototype stays stable. With that, we come to the last part where we actually then make the transition towards the contextual layer. Because to solve this task, if you have seen, we just need the adaptive layer. But in the case where all the cue patches will be red, we really need contextual information. So I have to know that I've seen this patch before this patch to know that I have to turn here to the left. We have just seen now in the first step how the adaptive layer will perform in this task. And it performs in the size, so this is just adaptive layer, that it will have a variety of actions for the different patches. And this is exactly what we need for the contextual layer. We can store these action perception pairs in the contextual layer and then select from the successful one for the successful trials to then guide the behavior, and we then apply on top of the adaptive layer the contextual layer. In this terms, in the DAC 6 version, we really see that we can learn this task with this underlying adaptive layer. So the conclusions of this predictive correlative subspace learning is that this prediction really serves as the unification for behavioral and perceptual learning. So it's really like we can take it as a basic principle. We have seen that balance between perception and behavioral learning is essential for the formation of the sensor-motor contingencies. And if we look at the switching paradigm, what we see is actually that we get stability through adaptability. So in terms that I really adapt very fast my weights, still I can get stability in the prototypes in the projection of the action towards the perception. So thanks very much for your attention, and thank you much for your attention.